Warning, this video will talk about compensator, but I'll not go into details, it's very abstract, so some explanations may not be good enough. Nonetheless, this chapter talk about the controller design, where the controller design, if you were to input a certain compensator, so if you input a compensator, you could actually improve a certain performance of the controller in a certain sense. Okay, so it's very abstract as I say, and let me see. So this topic will be related, very linked to your performance criteria. If you remember this 5 points over here, you're gonna remember. So for compensator wise, for high frequency, you're gonna talk about point 1, 2, 3, and 5 when it's talking about high frequency so-called application. For low frequency is 0.4. Alright, so there's a certain link in there. So I leave you to think about it, because all of this is actually, I've explained earlier, is talking about the bandwidth and such, whether it's stable or not. So these are all the things that talking about high frequency. If it's low frequency, yeah, I'm not gonna talk about it. So let's straight away jump to your lead capacitor and your. If you remember the lead and lag, the lead is actually the so-called the numerator, right? So the numerator, as you can see, the value of over here is larger than the value over here at the overall scales, right? If let's say let me see. Let's say your cutoff frequency is actually, where's my pen? Hold on. So if let's say your cutoff frequency is actually 1 plus, okay, S, let's say it's like 10, okay, and then if your alpha is like have to be larger than 1, okay. So 1 plus S, if lesser than 1 is like maybe 100, maybe like let's say I say alpha is 10. Okay, usually it's smaller than 10 but maybe I should put it 9 Okay, so 9 times this is actually your omega C, right? So omega C, which is 90 in this case, because 9 times omega C is 90. So if you were to take a close look, you have 1 plus 0.1 S, right, divided by 1 plus 0.01 S. And if my S value is, let's say, maybe like 1, okay, it's just an example so if S is 1, so 0.1, so I'll have 1.1 divided by 1.01. Okay, so if this is the case, 1.1 divided by 1.01, you're gonna increase a significant bit, 1.089, something like that. Okay, you're gonna so why do you want to increase a significant bit of not a bit, but rather than, why do you want to increase a little bit, not very big, not very much, or what? It's because you want to just smoothen the signal itself. So the purpose of this lead capacitor is actually to improve the high frequency behavior. Most likely is to increase the bandwidth of the thing, and to increase the phase margin. The bandwidth that he's talking about, I believe, is the 3 dB gain. If there is more lead, you have 6 dB gain, right? If you remember, if let's say I have 1 plus S divided by 1 plus S 1 minus S. Hey, what am I doing? S minus 1, S minus 2, S minus 3. So if I have this thing over here, right, if it's only one degree, it's actually 3 dB. If it's a second order degree, it is 6 dB, right? If it's 3 order degree, it's like 9 dB, and so on and so forth. So therefore, the more you are, the more gain you have in a certain sense at this point. So you have a more smoother graph in a certain sense, right? So therefore, it's talking about that's what you're talking about. I may be wrong, okay? So it's very abstract, there's no, yeah. And then the phase margin is just saying that more phase margin means better. So this is just the case, less resonant. Okay, so you just remember this 3 point. So the lead capacitor improve the high frequency behavior, increased bandwidth and increased phase margin, less resonance. That's all. And then it's usually alpha is usually more than 10, okay, and larger than 1. Alright. And then the phase angle is always positive because it's a lead capacitor. Alright. And then you can also remember this formula. And how you derive this formula? This formula is actually from this one, right? It's actually imaginary over real. So this is this one. So it's omega. This is actually omega, right? Omega divided by omega c. So minus away the denominator because minus away is tangent. So if you were to have this thing over here, this is actually the tangent rule. If you remember the tangent inverse A plus tangent inverse B. What am I doing? This actually equals to tangent inverse A plus B 1 minus AB, or 1 plus A. Yeah, it's this formula over here, right? So we're gonna use this formula. Okay, this is a formula that is not given in your test, and is also not given in any internet. Okay, this is something very close door even. So if you were to do that, omega divided by omega c plus, because it's minus, so it's omega c minus alpha omega c, right, divided by 1 minus AB, so I have 1 minus, because minus this term times this term will have plus, right? We'll have minus, right? This term is minus times this term, you have minus, so minus minus is plus, so omega square, and then alpha omega c square, yeah, correct. So this is simply what is being shown over here, just that I need to filter out this omega c out. So I have, I think you get what I mean. So this term is simply this one, exactly the same. Alright. So with these, this phase angle is maximum when this thing is equals to 0. So what it means is that when tangent inverse is equals to 0. Okay? And what it means is that if it's 0, if the phase angle is 0, this means that you have this is the maximum you can go. If you the further you after that very value, you are going to be unstable. Okay, so in the Nyquist plot way of saying, this is your minus 1, right? So this is exactly at minus 180 degrees. Okay, just exact. If you cross over, right, you become unstable. So this is some sort of that thing. So this thing, if it's equals to 0, tangent inverse 0 is actually 0, so it is like that. So you just rearrange, like it can become like that. So the purpose of this is actually to come out an equation. Alright. So you just rearrange on them, you have this, and then after which it will become like that. And then this is your final equation. So for lead compensator, what you need to remember is that it is for a low frequency gain equals to 1, and high frequency gain is equals to alpha. And the purpose is for high frequency, and then increased bandwidth, and then phase margin, higher phase margin. And then for lag compensator, it's the other way around. Alright, as you can see, low frequency is 1, this is alpha, high frequency is alpha, this is 1. So the equation is the same. This one is the same as this one. You should take a look. Alright, exactly the same. But this portion over here is different. The alpha over here is being switched over here. Right? So this is why we have a little different. And then nonetheless, for the lag, it's talking about trying to smoothen out, to improve the low frequency of the system, increase the gain of the system, and then preserving the same phase margin or having steady state and low a better steady state and low frequency performance. I think this one I just reading is like stupid lah. So you just go and read yourself lah. I'm not gonna talk about it. So I'm just trying to give you the brief concept on what the hell are they and what are the things that you might need to remember and memorize. So link lag compensators is this one over here. What is the difference from there is that when you want to improve gain and natural frequency, you use leak lag. Okay, if you have a gain and natural frequency and you feel that it's not good enough, then you use leak lag. Okay, this is the general formula. I think you know what you just memorize. These are all memorizing already. I cannot help you. Yeah. So yeah, this is just for the test itself. For future reference, this is not a good video. So I'll see you in yeah. So this ends the whole system on control, and good luck. Bye bye.